say? No piano. Maybe I'll fall into.
Did you say piano?
Yes.
You play piano?
I do.
Oh, wow. Did you go to the talk the other night by the mathematician, musician?
I didn't.
Oh, wow. He was amazing. This guy was a terrific violinist. He's played with, symphony orchestras, but he's also a tenured professor of mathematics at St. Mary's College in Maryland, which is just like ours, the same kind of school as ours.
Yeah.
And he was here talking about relationships between music and math, and he was talking about how Bach would take a simple melody, and then he'd play it, right? Then he'd essentially flip it from left to right. He'd flip it this way, or he'd flip it that way, or both, right? Mm-hmm. And then they played the two of them. It was really, really cool.
That's awesome.
Yeah. Talked about the physics of different kinds of strings and tubes and so forth. So he takes out this hose from your pool, right? If there's a filter that goes from your pool to your, or hose that goes from your filter to your pool, just this long thing, and he starts swinging it around, and he gets a tone out of it, right? No big deal. Mm-hmm. And then he plays taps by swinging it faster or slower. He makes the point that a bugle is just really like a tube, right? And he was swinging at a different rates, and he was playing a song just by altering the rate at which he was swinging it. Pretty amazing, this guy. Dr. David Kung was his name. Victoria, have you viewed your video?
Oh, no.
Yeah, you haven't? Okay. Okay. Yeah. Thought it came out pretty well. I'm sorry? Yeah, I didn't see the bee. So did you all recognize that the other day? There was a bee floating around here during Victoria's presentation.
Oh, yeah.
I was back there, and the bee was first there. I thought, oh, this bee's going to be on the screen, because he was kind of going in front of the iPad. And then he made his way up here, and I could see people were getting distracted. Then he was in on Victoria for a while, and he kept on coming back to her. But you stayed with it, so good for you. Good morning, Hannah.
Good morning.
Good morning, Jake. Okay, we have 8:30. Why don't we get started? Good morning, Psych Stats.
Good morning.
Who's ready for fall break? Yeah, we're already there. Great chance to get some REM. So it's hard to believe we've been going at this thing for a little bit more than 8 weeks, or I guess we're completing 8 weeks now. So we're making our way on there. I want to congratulate you on your excellent responses to Exam 2. That was a take-home written exam, and there are some really, really strong writers in this class, and that's a great pleasure to see. Now, every once in a while I get a clinker, and I didn't have any clinkers this time. They were all really nicely written, and some of them were absolutely exceptional. So thank you for your excellent responses. Hopefully people get those responses, or you got them through Blackboard. I don't know if people have already seen those, or if you have to sign on, or if you get an email. I don't know what it looks like from your side. I don't know if you get a response, but you don't have to go there now. And thank you for your good work on that. Okay, just as a heads up for all of your classes, midterm grades are due at high noon on Monday. So the professors are going to be working over these 4 days coming up for fall break to make sure that we get our grades in on time. So that will be true in all of your classes. And speaking of Monday, we also have our journal club session. And I think this is going to be really interesting. We have 4 Denisonian authors on this. Trent Edmonds, who is from our IT group, helped out with a lot of the computer programming in this particular study on place perception. And other authors include our own Dr. Harry Hept. And some people might know Jill Weeks. Does anybody here know Jill, who just graduated a few months ago, right? So she's doing a neuroscience degree now, I think at Pittsburgh, if I have that correctly. And you probably don't know Justine Hoke, but she was in Gabby's seat in 2009, and she graduated, 2011, and she graduated in 2012. So Justine is now at NYU doing some work with Psychology Lab, I believe. Okay? So we have 4 Denison authors on this. I think it'll be very interesting. It does speak to the issue of ANOVA, and we're going to be getting to ANOVA in a week or two, but we have quite a bit of work to do still in multiple regression. Okay? So speaking of Monday, one last idea. We'll just make sure that we're all checked in on this. This was a slide that we had on the first day of class, and so Monday is going to be the 19th. And we have Jake up for a presentation, so you want to make sure that you're on board with that. Is that looking good? Okay. And then just to look ahead to our remaining weeks, we have Karen, Vanessa, and Gabby in that order. Right? Does that all sound good? And then 1 week after that will be November 16th, and as I've mentioned, we'll have Angela Brown, who will be joining us from OSU. She'll come in and talk to us about narcissism. And then the following week is going to be Thanksgiving break. When we come back, early that morning, we will be joined by Julie Tucker, who is a 2009 graduate of Denison, so she would have been in this class in 2008 of her senior year. And Julie works with Dr. Laurel Kennedy in student development, and she'll tell us something about the stats that she does for the university. Okay? All right, and that will take us really through the end of the semester. All right. So that's where we're going for the next bit of time. I did want to pick up on, now that we have just a moment, I wanted to pick up on one other comment that was made about TED Ed when I asked you for feedback. It was largely positive. We extended a 3-hour grace period. And then one other factor that I wanted to see if we could explore, I wanted to show you what things look like from my side. Somebody said it would be nice if they could figure out how to collect all of their responses in TED Ed and put them into some kind of collection. I'll call it a compendium. And so from my perspective, these are all the TED Ed lessons that I create. So here's ours on multiple regression for today, right? And I can go into here, as I've done many times before in class. If I dial all the way down, something I hadn't shown you, I get a little option that says Download Student Responses, CSV, and I can click on that. Okay, and I can open it all in Excel, just so you can see what this thing looks like. Okay, and now I think it comes in sorted by, probably it looks like it's sorted by student, and it might be sorted by, something like their sequence. But I could highlight the whole thing, and I could go to data if I wanted to, and I could sort by any number of fields. I could sort by, question, and I'll get all the Q1s first, right, is the idea. So I'm hoping that maybe there's something like that for you, and then I could grab all of this, and I could paste it into some kind of a master Excel file, and say, well, this was my lesson on multiple regression, and this is my lesson on effect size, and this is my lesson on Cohen's D, or whatever the case might be, right? So I have all these different lessons that I could put in, and I thought maybe we could create a compendium this way, and I'm hoping you will go to TED-Ed now, and maybe we can learn from each other. Is there something like that CSV option that you have that might help us answer the student's question? The student wanted to create this collection or compendium, but I don't know how it looks from your angle. So I was here, and I had my CSV option over on that side. See if anybody can find something like that. This way, as you're beginning to study for quizzes or exams, or as you're just really looking over your notes, maybe you're headed to graduate school, and at some point you're going to be challenged with some issue, rather than trying to piece through, particular questions in particular lessons strewn all over TED-Ed, you'd have it all in one location. You'd have all your stats questions in one location. Is anybody getting anything like that? Do you get any kind of CSV option down here? No? Okay. I'm curious to see how it looks from your angle. I'll go back one. So do you get anything like this? You have something, and what is that for you? All of the lessons that you've completed? Is that how that works? Okay. And let's see, you probably get, I wonder if this is where we start to differ. So I can see how many people have responded. You probably don't get something like this. You just get this little upper part. Is that what you get? Okay. Okay. So maybe a suggestion that could be made to TED-Ed is for some way for you to aggregate all of your responses, right, or some subset of your responses. Okay. Anybody find anything else that was clickable in there that might help the student out who wanted to create a compendium? Okay. So if we figure that out, or if somebody in IT can help us out, then we'll go with that. But for right now, why don't we go ahead and move on to some conversation about your questions for today. So I'll open up a couple of things. Let me open up the 1014 PowerPoint. How many people found this PowerPoint to be helpful in responding to those questions? Okay, good. Hopefully you were tracking what I was doing as I was creating these questions. And why don't we start just with the first question. And in TED-Ed, the first question was asking you to make a distinction between multiple regression and multivariate regression, or multivariate analyses. And I saw some of the answers, and those were looking pretty good. So multiple regression versus multivariate regression. Anybody want to help us out with that? You can call up your responses if you want. Thank you, Melanie.
Multiple linear regression is the models the relationship between one dependent variable and like more than one explanatory variable. Okay. Whereas multivariate models multiple dependent variables.
Yeah, right. Okay, so whenever we hear multivariate, okay, we're really talking about having multiple dependent variables. And we haven't done that in this class, and you don't do that in Psych 200. I don't know if anybody here has done any multivariate statistics before. Is anybody aware that they've done multivariate statistics before? Maybe in another class or for a research project with a professor? Okay? So we will end this semester by talking about a small collection of multivariate statistics. Those are fairly complicated, but they're also really, really interesting. So we'll start out with the more humble case of having just one dependent variable and a whole bunch now of predictor variables, and that's going to be multiple regression. Okay? So then we ask people to go to Draw To, and maybe I can join us out here, or bring us all together in TED-Ed. I'll go to review the student work. Why don't I go down, I'll just open this one up. Okay. And I'll go to question 2, and I'll go randomly, sort of half the way down the page. Why don't I go to Vanessa? That's okay? Okay. So I've got Vanessa here. And go to question 2, and we'll go to the Draw To link. All right. So we've got the idea there. We're trying to predict one variable. We had a color coding there, that we were going to draw the variable to be predicted in blue. As we see over here, we have a couple of different predictor variables. So that's kind of cool. And this is also a way of thinking about factorial ANOVA. And there are actually formal mathematical relationships between factorial ANOVA and multiple regression. There's also similar formal mathematical relationships between regression and teaching, regression and ANOVAs. So those are all going to hang together. They're all linear models, but this is looking pretty good. Okay, and then we go on to, maybe I can stay with Vanessa. Maybe I'll go to the next question. Okay, and this is question 3. And now we're going to look at the region that's jointly predicted. Okay, she's got it, right? So that's the overlap. Okay, and this is kind of going to be like where we have interactions. Right? We can say that we might have an interaction effect. And who remembers hearing about interactions from ANOVAs in Psych 200? Okay, right. So we haven't talked about ANOVAs yet this semester, but if you were to take a Venn diagram approach to ANOVA and you had your predictor variable, predictor variables, plural, and your criterion variable, then you would have the interaction component right about there where Vanessa has drawn that. Okay? Okay? And so this is going to be an important idea. I'm going to show it in an animated way in PowerPoint. Okay. And I love the toggle between these two. I just find this to be, I can do this for like hours. Through the miracle of PowerPoint, right? Okay. So the important part about this is that we're trying to explain some variability in our criterion variable. And we have some redundancy here, right? There's some overlap. And that's going to be very important when we get into different kinds of regression models. That overlap is going to create all kinds of mischief for us when we start comparing different kinds of regression models one to the next. Okay? All right, and then we went on to question 4 in TED Ed. And question 4 is, now can we use another pen to have a third predictor variable? Okay, and that's going to be something like that. Okay, and this one has no overlap with any of the other two. Okay, so we have 3 predictor variables. 2 of them are intercorrelated, at least in part. All of them have some overlap with the criterion. Okay, all right, so kind of an interesting way to go. So this brings us now to question 5. Okay. And the idea was that if you wanted to go with a parsimonious model and you were trying to explain some variability in the criterion, and you have 3 predictors, but you wanted to be more parsimonious than having 3 predictors, you wanted to have 2 predictors. Which 2 would you pick and why? Can somebody help us out with that idea? There are a couple of pairings that work better than other pairings. Which 2 wouldn't you pick? Yeah, thanks, Karen.
X1 and 2.
X1 and 2, okay, and that's because?
They overlap so much that they don't give you much more information.
Okay, right. So they're doing, what X1 is doing for you is largely similar to what X2 is doing for you, right? Okay, they're accounting for quite a bit of, individually quite a bit of variability. Collectively, they explain a little bit more than either one alone, okay? So you can go with X1 and X3 or X2 and X3. Who's following that? Is that working for us? Yeah. We've got quite a display of birds out here today, isn't it? That's interesting. Okay, so any questions on that? Is that all intuitive? Yeah. Really very grateful to Venn for inventing that diagram. I think it makes so many complicated ideas very, very clear. You can imagine we could have done all of this just by having lists and lists and lists of numbers. And we'd have to eyeball them and say, well, isn't it the case that, the third list looks kind of like it overlaps with this list, but it looks quite a bit different from those. And now that we have this in Venn diagram, it's really, really quite intuitive. Okay, somebody want to help us out with question 6, which was writing the multiple linear regression equation expressed in z-scores. So how would that look? Somebody want to call that out for us? Maybe I can project. I'll go to somebody other than Vanessa. Here. And let me go to question 6. Okay, let me dial down randomly to, can I go to Hannah? Just, okay. I'm going to go to question 6. Okay. All right. So are people able to see that? Is that clear? Okay. So we have zy, okay, and that's perfect. That's exactly what I was looking for. So we're trying to predict the z-score on our criterion variable. And just so you know, if you take other stats courses, sometimes they'll put a little hat over the z. What does that mean, the hat over the z? We have it in a few of our slides in PowerPoint, but I don't think I've made a big deal out of it. What that means is the predicted value of y. Right? So there can be some confusion about different kinds of y's. There can be an observed y or a predicted y. And if you see this little hat, I'll draw it over here. So you'll see zy sometimes. That just could be the z transform of the y-score. But you'll see sometimes like a hat might have something like that. It means the predicted value of that. So the predicted value, and I wouldn't expect you to be able to put that in there, is going to be equal to some beta. And notice that she's got a beta 1, a beta 2, and a beta 3 for these different. Notice that she doesn't have any kind of an intercept. So we do have a type of y equals mx plus b going on here. How come she doesn't have an intercept? Did I kind of forget something? You don't have one with z-score, so she didn't forget anything, right? You could put a +0 there, right? But we're not going to have one. These b's could be pluses or minuses, right? And hopefully this is something that you had already understood, but in case not, I'd like to really drive this point home. When we get these different betas, right, these are the different coefficients associated with these z-scores. Let's just say that we have something like a negative 0.4 as one of our betas. We'll say beta 1 is negative 0.4 times z1. Okay? So that's what we have as our coefficient. And that's a z, and that's a z. Okay? What this would mean is that a 1 unit change in this is going to drive a minus 0.4 unit change in that. Okay? Is that working for us? Okay, so a 1 unit change in this, and when we say 1 unit, we mean 1 standard unit, and we mean 1 standard deviation. So if I were to move by 1 standard deviation on this variable, let's say that's an age variable, okay? And we have some range of ages. I'm older than you are, right? And depending on how wide that range is, maybe I'm 1 standard deviation older than you are, okay? So if I were 1 standard deviation older than you are, and we went from your score to my score, we would predict, as shown here, that we would go down on this variable by minus 0.4 standard deviations. Okay? So everything is in a standard deviation type of unit. Who's following that? Is that working for us? So it's really cool that we get the number of standard deviations and fluctuation that can be positively balanced or negatively balanced for each of these betas. Okay? All right. Any questions on that? Yeah? Okay. I wonder if we can do this. We've gone through that first a little bit. Let's stay with this diagram. And if we can, we'll see if we can have you do a little bit of thinking about taking this diagram and applying it to what you told me on the first day of class were your interests. Okay, so this is what I recorded on the first day of class. You can see your name here. And then you told me the information that is listed in category F, or column F. Okay? So I wonder if you can think of something. So for example, if we stay with Gabby, who's here at the bottom, she had an interest in behavioral and forensic psychology, right? So if we can think about taking Gabby's interest, we'll ask Gabby to think about that, and see if Gabby can apply that to, we'll ask each of you to apply that to this diagram. There's something in Gabby's case, maybe in forensic psychology, that she would like to predict. That's her criterion variable. Can she generate 3 predictor variables, okay? And might it be the case that those 3 predictor variables are plausibly diagrammed like this? Right? They all have some overlap, but predictor variable 3 doesn't have any relation to these other 2. Okay? So why don't we give you a couple of minutes to think that through. Right? You're going to try to come up with real-life variables that would be somewhat germane to this topic. And for each of you, you have a slightly different take on this. Okay? You can focus your variables on the topic shown here. Okay? So we'll give you a couple of minutes to think that through. Okay? I think Jake wasn't with us on the first day, so Jake, you can make up your own topic. Okay? All right? We'll let you think that through, and we'll see if we can get a couple of responses in a couple of minutes. It does take a little while to think through this relationship, particularly separating these from these 2. If you need to draw it out, that might help you. if somebody has a response there, I realize this might take a moment or two. Can you raise your hand so I can see where we are on this? Okay. Some folks have something. Okay, how many people have something? Kind of, sort of, okay. Karen, could I impose on you? I think you had one of the first responses. So can you, let's go over and remind ourselves what your topics were, and then we'll see if we can plug in some variables. Okay? So here's Karen, and she had abnormal and clinical. Was that where you were going? Okay. And so Karen's going to try to apply abnormal and clinical to this schematic. Okay?
So my predicted variable would be predicted recovery from depression. And
I'm sorry, that's your criterion? You're going to try to predict recovery?
yeah.
Okay, so that's your criterion. Okay. Okay.
And then for variable x1 and x2, that would be like some sort of talk therapy, like interpersonal therapy and cognitive behavioral therapy, might, if you had both of them, they might overlap some with the predicted recovery.
Okay, okay. That's plausible because actually any kind of therapy, if you're there's a bit of a placebo effect no matter what, right? Okay. So we're trying to predict recovery. We have two different flavors of therapy. Okay.
And then I guess for the third one, there would be some sort of medication with an SSRI, which might have less overlap with the
Okay.
other ones.
Right. Okay. Now that too might have a placebo effect, but at least that's not a talk therapy kind of thing. So okay. All right. So I think you get the idea. Gabby was kind of like this on it. Do you have something you want to try?
I was thinking predicting criminal activity would be a criterion.
Okay.
And so variable x1 and x2 would be something like history of like criminal activity and like maybe parental like abuse or something.
Okay. So this is the history of criminal activity, and this is whether you're abused by your parents. Okay. So those two probably overlap, and they predict future criminality. Okay. Level of education, okay? Yeah, you can imagine that level of education wouldn't necessarily be related to parental abuse, okay? Okay, I think that works. Okay, so we get the idea, right? We don't have to do many more of those, but yeah, you can see that the predictor variables might be uncorrelated with each other, or they might be correlated very heavily. Just to plant the seed, we have not introduced a term called collinearity. Somewhat confusingly also called multi-collinearity, but that will be coming up either in our next PowerPoint series on multiple regression or the one after that. We'll have a total of 3 lessons on multiple regression. For the moment, though, I do want to go into what's maybe newer territory for us and see if we can have somebody help us explain what, let's do, hierarchical multiple regression is. Okay, so this is multiple regression, and just looking at it, we couldn't tell whether that was hierarchical or not. So can somebody help us out with that? Hierarchical multiple regression. I think it came up once or twice in one of the articles that we read for Journal Club, but we hadn't at that point introduced it in our TED Ed discussion. So somebody help us out with hierarchical? Okay, thanks, Hannah.
It involves entering predictor variables in a specific order,
okay.
Depending on whatever theory you're trying to test.
Okay, yeah, so very theory-driven, right? And we're going to say that we think that we have not only these 3 predictors, right, but we also are going to enter them into our model in a particular sequence, with this one coming first, this one coming second, and that one coming third as one possibility, right? So that they go into a particular sequence. Okay. All right. And then can you, so let's say I put this one in, okay? That one goes in, and then this second one might go in second, and it will go in no matter what, even if it doesn't explain any additional variability. I wonder if I can grab this, see if I can, okay? Oh, that works. Okay, so let's just say this thing had been over here, right? It might be the case that it explains no additional variability, right? But it still goes in, and it might be the case that new variance explained here is going to be 0 because this red one is already in. Are you able to see that all the way in the back? Yeah, okay. This red one is already accounting for whatever the green one is accounting for, right? So we're not buying anything, but our theory specified that we put it in. We told SPSS to try to predict this variable by putting this one in first and then that one second. Okay, and SPSS will come back, and then we'll do this one third. SPSS will come back and say how much variance is explained by the model in its entirety, and how much variance can be attributed to each of these steps right along the way. So you'll still get a report on this one, even if it isn't doing anything for you. SPSS will still tell you that it isn't buying you anything. Okay, and that's very theory driven. Right? It might be that you're trying to test a theory with some data that you've collected in grad school, and that might be somebody else's theory. That might be your theory. Okay. Okay, so that's hierarchical. Then we also have stepwise. Can somebody help us out with that distinction? What that means? Okay, Victoria's got that.
Stepwise multiple regression environment is a computer program kind of just tells you what variable is responsible for the greatest proportion of variance, and then like what variable is responsible for the second largest portion of variance.
Okay, right. Okay, and when does it stop? Let's say let's say I have 1,000 variables. Do you know when that stops? That was right on. Okay, so let's say that we put in 1,000 variables. Okay, right. We're trying to predict this thing. Here I'm showing you 3 predictors. We could have had 1,000 predictors. Okay, so and if you're doing a hierarchical multiple regression and your theory has 1,000 predictors, all the predictors go in, and SPSS will tell you how much incremental variance each one is explaining for you. We'll come back to incremental variance in a moment. In stepwise regression, you might put in the same 1,000, but what happens is the computer will pick the biggest one first, okay, and it will take the second one. And after the biggest one gets in, it actually asks this question: is even the biggest one explaining a statistically significant amount of the variance? And you get to specify what statistically significant is. It always defaults to 0.05. That's our default in most of the sciences, not just psychology. But there's a little parameter somewhere in there in SPSS, and you can say, well, I want the cutoff value to be 0.01 or 0.001. But let's just stay with 0.05 for the moment. If this red one is accounting for 0.05, is significant at the 0.05 level or better, it's in. Okay? Then the question is, if we go to any other variable, and we ask, is there any other variable there that can account for a statistically significant remaining portion of the variability? Okay? And if the answer is yes, then that one goes in, and it tells us what the R squared is for that one, or what the incremental R squared is. So how much additional variance are you getting there, and is that a statistically significant benefit to the model? If it is, it's in. Then let's say we go to a third variable, and I have variable 2 shown here. Let's say variable 2 actually is explaining some variability that the other 2 are not. Maybe you can see that right here. And I'm getting a little bit of incremental variability. Let's just say that's a non-significant fraction of the variability. Then that variable 2 doesn't make it, and everything thereafter doesn't make it. Right? So the computer basically puts them all in rank order of which one's explaining most, the next most, and it stops as soon as you get to a level of your variables that are not individually explaining significantly more variation than the current model has. Who's following that? Okay, that's a little confusing. Does anybody want greater clarity on that? So what's really cool is you can have exactly the same data set, okay, and you can have exactly the same criterion variable and predictor variables, plural, right? But you can wind up with different kinds of equations coming out of your multiple regression based entirely on whether you specified a theory in advance or whether you're using this computer-based method of stepwise regression. Okay. Questions on any of that? Okay. All right, so I've already alluded to this idea of order of entry. Why don't we go down and spend some time on that? Just a couple of icons here. So here's a fellow very seriously associated with theories, okay, right? And so this is kind of our reminder about the hierarchical approach. At one point, Newton was asked about how he understood space, and he said that he had no hypothesis about space. He went with hypothesis non fingo, very data-driven, okay? So that's what we have here. And just to finish up one question on that, we did try to make a connection to top-down and bottom-up processes. Who remembers hearing about top-down versus bottom-up in Intro to Psych? Probably all of you had it at some point. Okay? So which one goes with which here? Which one is top-down? Which one is bottom-up? Hierarchical And stepwise go with which of those ideas? Okay, thanks.
I said that hierarchical corresponds more closely to top-down, whereas stepwise corresponds to bottom-up.
Okay, right. And so can you unpack that a little bit for us?
So top-down is basically knowledge-driven processing.
Okay.
And with hierarchical multiple regression, you have a theory that you already have a theory that you're trying to see if it's accurate. So you already have that knowledge and you're using it to craft your regression, whereas with stepwise, bottom-up is more stimulus-driven, so you're just kind of exploring the data to see.
Yeah, right. Well, we can think of stimuli, by the way, as forms of information, forms of data, right? So we're getting, in this room, we can figure out how to navigate it because we have stimuli out there that are basically pointing to regions of space that we cannot enter and regions of space that we can enter, right? So I like the idea that you put stepwise together with bottom-up. I think that works really, really well. I had a great example about a week ago of a top-down driven finding in science, and that was the discovery of planet Neptune. Right? Wouldn't somebody want to remind us very briefly how that story went? How did we discover planet Neptune? Yeah, thanks.
Was it the very small but very reliable data that wasn't adopted from?
Right, okay, so very small but reliable effects. You can think of a planet's orbit as being something like a regression line, but it's not a linear regression, it's a elliptical regression. And there was a systematic departure for that. Now, I walked in this morning. It was a spectacular morning. It was so clear, and it was probably, I must have been walking at about 5:45. I got here at 6. It takes me about 15 minutes to walk in from my house. And the sky was so clear, but there's no way that you could possibly see Neptune. If Neptune were up there as a very faint star, you could say that is data-driven, that is stimulus-driven, right? But instead what had happened was somebody was able to track where Uranus was, and it wasn't exactly where it was supposed to be. So they used a theory to derive what might be pulling that thing off of its orbit, and now we can use that theory to capture some new knowledge about the heavens, so to speak, and we can use our hierarchical regression to see how our theories are doing and to test those. Okay? All right. Let's go into some of the confusion that arises, okay, about when we use these two different ones. So actually, as we can see here, it depends on what we want to accomplish with our multiple regression. If you want to test a theory, then hierarchical is clearly the way to go. If you want to explore a data set, you want to go with a stepwise. At least that would be one way to go. What is a possible limitation in going with stepwise? Other than it isn't theory-driven, there are some other hazards you can get if you go with a stepwise approach. Somebody want to unpack that for us? Okay, thanks, Karen.
Maybe your second and third predictor variables account for the same amount of variance on their own, but the second one, it was shown in the Venn diagram, wouldn't account for as much additional variance for the first predictor variable.
Okay, right.
So it might not be included in the model at all, which might be a problem.
Yeah, right. Okay, so I wonder if I can give you, very nicely explained, I wonder if I can give you an example of that. Frequently at colleges, people try to predict how well you will do. So if you can think back to when you were high school students, they want to figure out how well will you do if you come here. And if we were to accept you at Denison, would we be putting you at risk for not finishing? We'd like you to come. We'd like you to be successful. We want you to make it through to the other side. And if you weren't a strong student in high school, then we could say yes to you, but we might really be putting you at risk, and that's not good for you. That's not good for the university. So we want to figure out who's going to do really well. And a couple of predictors would be your high school grade point average. Okay, that's one predictor of how well you would do here academically. Another one might be some standardized test scores. So we can look at those two and figure out which is the better predictor. Well, sometimes people will use multiple regression and will put in, for example, high school GPA as a predictor, and then they'll add to that their prediction based on SATs or ACT scores, and we'll say, well, that doesn't really bias very much. But that's a little bit unfair because you could just easily have put in the SAT score first and then have concluded that maybe your high school GPA doesn't buy you very much. Who's following that? Is that working for us? Yeah. Okay. Okay. So all different kinds of combinations here. And I think Karen has spelled that out pretty well for us. In the time that we still have about 15 minutes or so. Okay, we were talking about order of entry. Okay, and we have some of these issues. Right? We've just more or less spelled out. It depends on what gets into the model first. Okay, that's a really big issue. Okay. Let's see if we can get to some distinctions between hierarchical multiple regression, stepwise, and simultaneous. So can somebody help us out with simultaneous multiple regression? It's a third variety that we have. Okay, thanks, Molly.
Simultaneous is when all the predictor variables are entered into the equation at the same time.
Okay, right. So how do we figure out what's what there? So that's perfect, right? It's, what you see is what you get. It's got the word simultaneous in it, so they all go in at the same time, but they all go in simultaneously. But as opposed to going in some kind of order, the order could have been driven by theory, hierarchically. It could have been driven in a stepwise manner based purely on the data, however random those data may have been based on the sample. Okay? So if they're all going in simultaneously, what values are associated with each of those? This is a little bit complicated. All these variables go in simultaneously. Okay. What values are associated? A little bit tricky. The value that's associated with each of those is the, if you will, the unique contribution that each one makes to the predictor variable. Okay. So we'll find out the unique contribution. And sometimes a picture will say 1,000 words here. Okay, so let's see if we can dial down. And if you want to be on this with me, because some of this is going to be, there will be a few small letters here that'll be a little hard to see. So I'm on the 1014 PowerPoint. If we can go to slide number 47, I'll make it really big up here. Okay, and we'll see how this works. So we'll start out with the simultaneous multiple regression, which is also called the standard multiple regression. Okay, so this is our third type of multiple regression model. And just to unpack things, we're going to do this a few different ways. We're going to look at diagram A, and we're going to look at diagram B. And A over here has a lot of variables. As you can see, we've got the dependent variable, and we have three different predictor variables, which are independent variables, 1, 2, and 3. So far, so good? Working for us? Okay. And what's cool is they've now taken these lowercase letters, and they've assigned a lowercase letter to the different areas of overlap. Okay. So what we can say here is that if we were to try to predict this, and we put in our three predictor variables, and we ran a simultaneous equation, and this is all spelled out this way, the unique contribution that's coming from IV number 1 is in area A. Okay? Now, note that IV number 1 actually overlaps with the DV in both A and B. Is that working for us? Okay. But what we have is A only, as what will come out of the SPSS value for you. Okay, so if you were to run a simultaneous bit and you had SPSS output, you would have a first or a zero order correlation. They will tell you in the output just how strongly IV number 1 is correlated overall with this DV, but on the multiple regression side, it would just give IV1 credit for area A only. Is that people following that? Okay, so it's a bit informal, but I do like that phrase, how much credit does IV1 get? Okay, and IV1 is only going to get credit in this particular model for area A. Had this been hierarchically done, right, you could have specified that you want IV1 first, and had that been the case, then IV1 would get credit for A and B. Okay, but if you run it in a stepwise, well, IV1 will show up only if it beats the other guys, right? And only if it's adding something that is statistically significant. And then if you do this in a simultaneous model, you would get only A. Okay, is that working for us? Okay. And then IV2 is going to give us only C uniquely. That is its unique contribution to the dependent variable. Right? And IV number 3, which is down on the bottom here, this bottom circle, will give you only E uniquely, but E and D collectively. Okay? So it's really cool when you get the SPSS output, and probably our third of 3 sessions we'll start playing with SPSS. We like to get all the conceptual work down first. One of the very first boxes is just the straight correlations between any one of these variables and the predictor and the criterion variable. Right? So if you were just to do a simple equals Carrel or equals Pearson inside of inside of Excel, what would that value be? And that would be, for example, for E3, areas D and E for variable 3 on the dependent variable. Okay? But then you can now unpack that and look at the simultaneous equation. That would just be E. Who's following all that? Okay? That's a lot. Is anybody confused by that? But thank goodness for Venn diagrams. I mean, at least Venn diagrams give us a shot at all this complexity. By the way, one other interesting factoid. All of these correlations that we're talking about are simple linear correlations. So in area E, we're talking about the linear correlation that is uniquely contributed by variable 3 to the dependent variable. Okay? You can imagine that somebody could be clever enough to create some kind of multiple regression where the regression relations are nonlinear. Okay? So now you have multiple nonlinear regression. But for our purposes, we're keeping it all linear. Who's following that? Is that working for us? Okay. Okay. So here's just a review of what we've gone over. These are the components that are unique contributions. Right? And you will be able to get out of your SPSS model the total amount of variability explained by this ensemble, this constellation of predictors, right? And they'll give you the R squared, but then they'll also break it down and say, well, IV1 is just giving you this uniquely, and IV2 is just giving you that uniquely. So you get both pieces of information there. What is the group doing overall, and what are the unique contributions? Okay, so that comparison between what I have here in A and B is for the simultaneous case, or the standard case. Okay? We're going to keep this just as we have it, and why don't we take a peek at how this would look differently if we were to move to now a hierarchical model. Okay? So same kind of arrangement, okay? And exactly the same predictors, right? But now we're going to do a different order of entry as specified by some model that maybe you've been reading about for your senior research or whatever the case might be. There's going to be some type of theory that's driving this. And let's say that IV1 enters first. It will get credit for A and B. Okay? Let's just say that your theory force fits IV2 into there next. Okay, so it's going to get credit for C and D. And then we have E left over here. And that would be reported, again, whether it was statistically significant or not. Okay? There's no contingency there on statistical significance in the hierarchical variety. Who's following all that? Yeah? Anybody confused by that? Okay, can we do one more? So we'll start trying to explain area A, but we'll go now to a different variety of multiple regression, and we'll keep this our stepwise. By the way, there are still other kinds of multiple regressions, but we're going to be talking about these three. Okay, so here's stepwise, and I think it was Victoria who was explaining to us that the computer will go looking about and trying to find what is statistically correlated with what. Okay, so let's just say that IV1 enters first, it gets credit for A and B. Okay. IV3 will get credit for D and E in this particular case, and poor IV2 gets credit only for that, and only if it's statistically significant, right? Only for area C. Okay. Now you might say that's a little bit unfair to IV2. It's not getting very much credit, right? Okay. Even though it seems to be doing as much work as IV3, but for whatever reason it got in there. IV2 has the disadvantage of being very heavily correlated with IV1. Okay? So that put it at a disadvantage for explaining incremental variance. And that's something that through the years has tripped up the students a little bit, that there's this idea of R squared, they tend to get that, right? And then the newer idea of incremental R squared, okay, is the new wrinkle that we add here. And it takes a little bit of practice to get used to that. All right. By a show of hands, how many people are following those different kinds of multiple regressions? Yeah? All right, really good, really good. Why don't we do one more big idea for today, and that's partial correlation. Okay? And I think one more time we'll have Venn diagrams say 1,000 words for us. A picture really can say 1,000 words. And I think that these particular concepts are mislabeled. There's something called a partial correlation and a semi-partial correlation. And if it had been up to me many, many years ago when these terms are being developed, I might have labeled them the other way around. What we're going to do now is partial out some of the variability or have a semi-partial correlation. Okay? So we have a couple of different ways of going here, but in the interest of time, why don't we just take a look at this one. So if you're playing along on your computer monitor, I'm on slide number 56. And what we're going to try to do is we're going to try to predict this variable that's called the dv, and it says cred now. Let me give you a little bit of background on that, since I'm sure that's pretty unclear as to what cred now is. At our school, almost all students take 4 classes, and sometimes they might take an extra 1 credit class or something like that. But at many other schools, particularly community colleges, people take greatly varying numbers of credits. There are full-time students there who might be taking, 16 credits like you are. But there are other people who are just, they're like me. They've already got their career going, and they show up for one class in that semester, or maybe 2 classes in a semester. Sometimes there are stay-at-home parents that will go to a class for 1 or 2 classes a semester. So we can try to predict how many credits they're taking now. Okay, let's say that you're Julie Tucker for a community college. Right? You're doing the statistics for that college, and you're trying to figure out something about your student body. How many credits are they taking? You can ask whether or not they work at night. Some people have night jobs. Other people don't have night jobs. You can try to use their status or the number of hours they work at night as a predictor of how many credits they're taking now. Who's following the variables? Does that make sense for us? Okay, so up on top we have the simple dimple correlation that you might have done even in the first week of Intro to Psych, right? We're just going to take an equals correl between the values that we have in our number of hours worked at night and the number of credits that you're currently earning at the community college. Okay, that's a simple equals correl, and we get some value there. Like maybe the more hours you're working at night, the fewer credits you're taking is what we would get there. Now what we're going to do is we're going to partial out something, right? We're going to try to remove some other influence that we might have. There's some third variable that we want to put into our model and pull that out of both the criterion, how many credits you're taking now, and the predictor variable. Okay, and so the reason this is a sectored disk is we removed the correlated variability with some kind of third variable, and we've done that over here. Who's following that? Does that work for us? Yeah, we've held that constant. We've partialed out that fraction of the variability. And we're asking, now that we've controlled for or partialed out that fraction of the variability, how much of the variability in our criterion variable can be accounted for by our predictor variable? Okay? The critical thing about this is that it's been partialed out of both of these circles, both of these variables. Yeah? Is that working for us? Okay. And that's called a partial correlation. Okay? We've partialed that out. If I can contrast that with a semi-partial correlation, okay, so way up top we have the simple dimple 0 order case. That's what you did in Intro to Psych. Now we're partialing out the third variable from both of these, predictor and criterion. And then another variation is that you might choose to just partial it out of the predictor variable and leave the criterion variable exactly as it is. And that's called a semi-partial. So you partial it out of one of the 2 variables, but not both of them. Okay, and in that sense, it is semi-partial. Okay? And you can see that we still have the same overlap in these cases, but we have this fraction of the whole versus this fraction of a segment. Right? So proportionally speaking, this number is going to be bigger than that number. How many people follow that? Right? Because we have, well, we'll say that's 3 parts out of 30 versus 3 parts out of 40. Yeah? Okay? So weirdly, your semi-partial is going to be this smaller fraction of the whole. Okay? Okay, so that's partialing. And this, again, is a little bit like what we just mentioned for simultaneous regression, and that is that this tells us about the unique contribution to the total variability. Right? It's unique contribution to the total variability. It might have more overlap, as you can see way up there, but that wouldn't be unique because there's some other variable that shares that. So if you wanted to know the unique contribution to the total variability, the semi-partial would be what you want. All right. Questions or comments on any of that? Well, that was a lot. This was a PowerPoint that had 60 slides in it. All right. So thank you for your TED Ed responses. And we're at 9:19, so why don't we give you a minute off for good behavior. I hope you have a wonderful fall break. And we'll look forward to our session on Monday, where we'll have a journal club with Dr. Harry Hef's article and Jill Weeks as a co-author. And then we'll hear from Jake on the presentation. Right? Have a great fall break.
I haven't. Yay. I'm retired. So Vanessa, ride the ride? No, the ride off. Okay. All right. Yeah, no problem. Anything, just let me know.
Oh, sorry.
People live. I might just run down and just chill out there and see how many people actually show up, but I kind of think we're gonna cancel. Yeah. I don't feel like setting up the net if there's like 4 people. Yeah. Yeah.
Do you have a piano concert? Are you doing?
I don't.
You don't. Are you a minor or something?
No.
Okay.
I'm not. I just kind of do it for fun. I played for 7 years, and then my piano teacher moved away, and I didn't get a new one. So I started up when I quit singing because I used to do that.
You used to do that. Okay. No, I may have mentioned I occasionally teach a seminar here called the Cognitive Neuroscience of Music. Yeah. So.
Yeah.
All right.
Oh, feedback on my paper. I do give you permission to use.
Oh, that was you?
Yes.
Okay, straight up, I don't know if you can see it, I turn on anonymous grading.
Yeah.
So I don't know who I'm speaking to, but okay, thank you very much. That was beautiful. Absolutely gorgeous.
Thank you.
Yeah. So are you applying to graduate school this coming year?
Yes,
Okay,
that's
good.
the plan.
Oh, wow. Somebody's going to be lucky to have you. So.
Oh, thank you. I appreciate that.
All right, see you at 12:30?
All right.
All right.